Hello, good day. Welcome back. Today is day 18. We are on learning on embedded system design on ARM Cortex M4. I'm sure you are revising the previous sessions and you are getting yourselves familiar with all the registers, the different peripherals, and the bus connections where each peripherals is connected to, and all the registers that's associated with it. If not, please go back and revise yourself so you can be more familiar with and you can catch up with all the upcoming sessions. Today is day 18. We're going to learn about the implementation of task schedulers. I divided this into two parts. Today is part 1. These are the sections you will learn about today. You're going to learn what is a scheduler and how it is operational in terms of microcontroller usage. And you're going to learn how to create that scheduling using the SysTick timer. Before going in, I would like to tell a little bit about ourselves. I'm representing A2Digi. It is a startup by Anbukarasu brothers, my brother Alex and myself Arul in 2023. If you are wanting to get your website developed and built from scratch, please do contact Alex. He's very an expert and very good at website design, and he will get your website running within no minutes. Both of us gathered 20 years plus in the industry, and we would really like to put it out there to help you all so you can also be molded into a better professional. Our mission is to convey our knowledge and our experience that we face so far to help you out there, we living there, and it's to convey to at least 100,000 future professionals through our online courses. The main advantage is you can learn from it from anywhere you are and at your own pace. So that's a very good point of it. A little bit about me. I'm Arul Prakash Anbukarasu. You can call me as Arul or IPI, as persistent as I would like to be to share my experience and my knowledge to you all so you can also be a molded better professional. I have 20 plus years of experience working in various industries in Australia, in Italy, in Singapore, and in India, majoring some of the industries where renewable energy sector in the solar and wind energy conversions, the power systems that's associated with lead acid batteries, the network embedded systems that's connected with the ATMs, the teller cash registers and the point of sales, banking automation systems, and smart parking operations. And my expertise lies in here with embedded systems, VLSI, and project management. I got small announcement to make. I divided this into two categories as YouTube viewers and internship professionals. In order to be eligible to get a free East certificate, you got to attend at least 28 classes or 28 videos. Part of YouTube regulations, the videos can't live there forever, so it has to be removed after 2 or 3 days. In case if you have missed out one session and if you want to go back to recap, unfortunately you won't be able to do so. That's why I personally recommend you and advise you to join in one of our internship programs that will lead you to acquire an internship certificate. And that internship certificate is worth a lot in terms of value and time and everything, because once you step into that industry, you will work with senior engineers and they will consider this as an invaluable experience because you put your hard work already put in there and you learned about the new microcontroller and all about it, so they don't have to give you the fundamental training, so you will be up and running straight away. So the program managers, the project managers will love you so much because you did this hard work. Not only that, you'll get a separate login to log into our learning management system portal, so you can go through each and every day session. Once you finish one session, if you click on complete, that will count to your attendance. Once at the end of 30 days, after you go through the whole videos of 30 days, then it will auto-generate your certificate. Excuse me, I had to sneeze. Excuse me, beg your pardon, sorry. Not only that, you get unlimited access to all the course contents. That includes all the PDF materials, the source codes, and all the manuals, the reference manuals, the data sheet. It's unlimited, it's all yours. And also, you can pause the video, and if in case you missed a couple of sessions, and if you want to do a revise, you can go back because it's all yours to keep, and you get unlimited access. So you can pause, you can rewind, you can forward, whatever you want to do, it's all yours. And if you get stuck in the learning process, please contact our backend team. They are a friendly, lovely team, and they would be able to help you to make you move along in your learning curve. These are all the materials required. So if you haven't bought already, please do contact Pantex Solutions. They would be able to help you to acquire all of this for your learnings. They are a big manufacturing company, Pantex Solutions, and they have a friendly team out there as well, and they would be able to help you to get all of this. The more you spend time on hands to learn and experiment yourself using hardware, the more knowledge you get, and therefore you would be able to use it and come up with your own design. And as I keep saying, the materials won't stop for the usage of this series alone. You can take this and you can build your own design, and you can use this in your own project. So it's a money well worth spent. So please do contact Pantex Solutions to get all this. So shall we get into the tasks that we've been talking about in a lot of sessions and see what is in it in the schedule for us today? As you can see, that's a task, and there will be schedules of it. So let's jump in and learn ourselves to see what the day unfolds for us. First, we're going to learn about scheduler. What is a scheduler? You may be knowing with different definitions about it with different contexts, but this is in terms of microcontroller. The scheduler is a program that manages the execution of multiple tasks or processes. So in a program, when there are different functions, when it has to run simultaneously or one after the other, so the scheduler looks after all that execution of those tasks and process. So it comes in a form of a program and manages those running tasks. It is responsible for determining which tasks should be executed next, and for allocating system resources. It allocates the CPU time and also the memory to the tasks. The scheduler plays a major role. Whenever a task comes to the controller, it knows how much space or memory it has to allocate and how the running speed of the CPU time it has to allocate. A scheduler also uses an algorithm. This is a scheduling algorithm to make the decisions of the memory allocations and the speed, which can be based on different factors. One of the factors will be the priority of the tasks. And also you can use what is a new system. It's called round robin scheduling. If you are good sports followers, like even instantly if you follow cricket or in tennis, sometimes you can hear this word about round robin in the first stage. And if you're not a sporty, and you would also hear this in round robin in other tasks. It's nothing but it's a way of processing the tasks that you will learn shortly. Now let's move on to learn what is a task. We know what is a scheduler, but what is a task? A task is a small piece of program or a code or a function. It's written to perform a specific job. Inside the function, it's written to perform a specific job. When it is allowed to run from the CPU, when the function calls and it started to run from the CPU, and it solves the purpose of running for a specific job. So that's what task is. And every task will have its own stack. Like in function, you have a common stack, and you push and pop and those instructions. But with task, the task will come with its own stack to create its local variables when it runs from a CPU. And when the scheduler decides to preempt, that means it's changing the value from if it is running on low priority tasks, and when suddenly a high priority comes, and the microcontroller has to stop that and release for the high priority to work. That's a preempt. A scheduler first saves all the context of that state into a private stack, so that once it finishes the highest priority, it has to come back, return back to the low priority to work. So it saves all those context in that private stack. In summary, task is a piece of code or function. When scheduled, it never loses its state unless if you deleted the task what you created in the program, then you can't use the task. So that's what task does. Task is to perform, to operate a specific job. So that's what task is. Now let's move on to learning about scheduler implementation. How to implement a scheduler. Let's think about implementing a scheduler which you have multiple tasks. For example, today we're going to learn about using 4 different tasks and how we're going to link those tasks in your program. So we're going to learn to use it in the round robin way, in the carrying out those context switching. You will learn about what is context switching in the next slide. So we're going to use this round robin scheduling method with the time slices that are assigned to each task in equal portion in a circular order. We will use sysdig handler to carry out, so that's why we covered the sysdig earlier. We're going to use that, and we're going to implement with the help of sysdig, we're going to implement the scheduler. This is RR scheduler. RR stands for round robin scheduler. Round robin is nothing but it is one of an algorithm that is used for scheduling in computer operating systems to share the CPU time evenly throughout the process. Being a multiple process, as you know, it runs in 2 different modes. The processor runs on a thread mode and on a handler mode. So whenever there is an interrupt, it stops the normal operation in the thread mode and immediately it jumps into the handler exception mode, and it runs those processes. So all these tasks will be assigned to a fixed time. So every task one will be, we're going to learn about different tasks in this program. So everything will be allocated with a specific time. And that is called as a time slice. Also sometimes it can be referred as a time quantum. Both the same meaning. It's a time slice. So that particular task is suitable for only to run on that time when it executes. So once it overlaps or once it goes above the time period, then the task is moved back to the queue. So therefore, if for example, if the task one is set for only 1 millisecond, it will run for that 1 millisecond, and if it needs more time to finish the job, it simply goes to the end of the queue. It won't wait until it finishes, because the time set is only for 1 millisecond. So it will jump to the next task and it will operate that and start and run that. And if it finishes on time, then it will move to task 3. If not, task 2 will go and sit in the queue again next to the task 2. So again, it will come to task 3, and that's how it operates. And if it doesn't finish in that time period, it goes and sits in the queue. So the round robin is nothing but it goes task after task after task in a listed form, in a queue format. It doesn't go back to the main program. As you know, it will execute for that time period, and then it goes back and finishes all the tasks before returning to the main program. So this process, until tasks have had a chance to execute, that's how it operates. So the interrupts are signals sent to the CPU by the hardware or the software to cause a current task. And this can be temporarily suspended and a different task to be executed. So that is the example it's given. We're going to use 4 tasks today. Task 1, it will start and it will pause at the end, and whenever a new interrupt the second task, the time allocation stops, it will save those contexts in a primary stack, private stack pointer in task 1 inside, so that when it finishes task 2, it can come back and do its operation. So that's why the contexts are saved. So that's the purpose of the task itself, because it has its own stack. So we're talking about the user stack and linking how the users, by definition, how they send the task and how it's been tasked. As I said earlier, in this today's session, we're going to learn about using 4 different tasks and how you're going to link that with the stack. Each task will come with its own stack. So the T1 will be linked to stack T1, T2 will be linked to stack T2, likewise T3 will be stack 3, T4 will be stack 4. And how the stack pointer selection are chosen in the operation mode. As you know, the stack pointer has 2 different modes, the PSP mode and MSP. The PSP is the processor stack pointer, and MSP is main stack pointer that you learned earlier in the coverage of the stack pointer. So once, in general, everything will be by default. You can have both modes in the stack pointer, but if you want to use for the handler mode, when the sysdig handler happens, then you need to define that in the program. So initially, in the thread mode, every stack is linked to the stack, to its private stacks, the T1, T2, that will be in the processor stack pointer with the thread mode. So whenever an interrupt happens, it jumps, it halts from there, and it saves those context into that private stack and does the task 2. If it wants to do jump to T3, it will save all the context of this task 2 into this private stack, and it will go to T3, likewise T4. So when interrupt occurs, it will halt this and it will go to the scheduler, that is the main stack pointer, to the handler mode, and it will operate and then come back to finish all the tasks. So this is how the selection happens. Initially, it will start with the thread mode in the PSP, and once the interrupt starts, then it will jump, it will halt and save the context here and then go to the handler. So that's the basic difference between a function and task. In function, it will have a common stack, so you can push by stacking and then go to the handler, and then pop instruction will get the data out. But in function, that's a common stack that you're going to use. But in task scheduler, every task has got its own private tasks to save all those tasks into a private stack. So that's the main difference between task and a function stack. So how this stack is assessed in this example. For example, if you go to the stack assessment, we know the STM32F411 has 128 kilobytes of SRAM. It will have a start address and the end address. So the stack, as you know, the Cortex M4 STM32F411 is a full descending order in the stack that you learned very early in the piece. It is situated in the vector table, so all the stack will be, the start of the stack will be at the base, so it comes as a descending order. So everything, now we are talking about the task scheduler, so everything is going to be allocated onto a time specific allotment. So in this example, every stack is allocated, every task is allocated to perform that operation in 1 kilobyte time. So that's what, and also the space for that is allocated as 1 kilobyte. So at the end of the SRAM in, the start of the task 1 stack start, and at the end of the T2 start, the T1 ends. At the end of the T3 start, the T2 ends. So this is how it operates. And this is all the private tasks of the tasks. And if it has any other interrupt that happens, then that will be scheduled and put into the private scheduler, those other interrupts. And next, we're going to learn about how the scheduling policy selection happens. So when it knows that you need to schedule all those tasks, so how this will be done in round robin fashion. So we'll be using round robin fashion for a preemptive scheduling, meaning if higher priority comes out, then it has to halt and save all the context and go to the scheduling policy. So we starting with 4 tasks in this example that you're going to learn. Everything is set for 1 millisecond operation in the interval of 1 millisecond. So there is, in the scheduling, there is no priority. So there is no a set priority. So it will run with that period of time, and then if it can't finish, it will save all that in the private stack and move on to the next stack. So we use sysdig timer to generate those exceptions for 1 millisecond. We already learned from previous session how to generate that 1 millisecond, and we used a formula to generate that, and we're going to load that into the load value register for 1 millisecond to run the scheduler. So this is how the operation going to happen. Task 1 will run for 1 millisecond. If it can't finish, then it will save everything into the private stack of T1, and then it will go to T2. It will run for another 1 millisecond. If it finishes, it will go to T3. If not, it will keep. So likewise, the round robin. So it happens in like a loop fashion. So one after the other, one after the other. If it doesn't finish, it simply doesn't go back to the main program, but it will go and join at the end of the queue. The T1 will start, and then the T2, etc. So just to recap what the scheduling is again, the scheduling is nothing but it's a program which takes the decision of preempting of the task that runs from the CPU and takes the decision which task should run on the CPU, sort of thing. The scheduler also uses a particular scheduling algorithm to make these decisions. So in that time, it can be used as whether it's a priority related task or a round robin scheduling. There are a lot of scheduling out there, but round robin is one of the most widely used. So that's why we're going to learn about round robin scheduling in this class. Now let's change to learn about, we've been reading, or I've been saying about context switching so far. So what is context switching? Context switching is nothing but it's a procedure of switching in and out, like when it changes from task 1 to task 2. So switching that task period, it's called switching, context switching, coming in, coming out of that stack to run a task. That's called context switching. So context switching is nothing but it's a procedure of switching out of the currently running task from the processor after it saves the particular task execution context or state, and switching in the next task to run the CPU by retrieving the past execution context or state of the task. Every task will have its own state, and that state will be saved into a primary private stack, and this is what it explains. Switching in and switching out. The switching out refers to the retrieving of data. The switching in is for the saving in. You're coming in and to the save those tasks. Okay. Next, we'll go into learning about how you can execute that context. So what is an execution context or a state of a task? As you know, in our ARM Cortex M4, the processor core comes with all these registers, the general purpose registers, GPR, the ALUs, the special registers, and the status registers forms the processor core. It will also have the debug unit. It will also have the nested vector interrupt controller, the memory protection unit, the system control block, and the floating point unit. So this is all represents the execution when you write that program, compiling and then changing to debug. So this is what you have, and then those core registers form the operation that it makes you to enable those functions that you already create in the form of tasks. So likewise, you will see in the stack of registers, register R to R7 written as the lower registers. These are all the general purpose registers, R0 to R12. But in that, R0 to R7 is considered as the lower registers, R8 to R12 is for higher registers. And register 13 or the SP, the stack pointer, as you know, stack pointer has two different modes, the processor stack pointer and the main stack pointer. And there is a link register LR, it's on round register 14, and there is a program counter on register 15. The link register is as we gone into lens to learn about it earlier, the link register will have all the addresses of a particular register. So you link that directly to whenever an exception handler comes, you go to that particular location and then it performs it and comes back. So that's where the link register is used. And then there is a register below the program counter. It's called PSR. It's a program status register. And these are all called special registers, the program status register and the exception mask register, the primary mask and the fault mask, and there is a control register. So this is the whole set of registers, all the core registers to perform your compiling and debug. And this certainly forms a major role in performing that operations. So now we're going to learn about the context saving and retrieving in the round robin fashion that we were learning so far. So if you go to this flow, first the T1 will be run, the task 1 will be run, and then if you want to move on to task 2, you have to save that context so that when it comes back you can work on the saved data. So that's how the flow works. Before jumping on to T2, it will save the context of the T1 inside the T1 task 1 private stack. This is called pushing, context saving. So you learn from the previous sessions that this is how in a function when it happens, it will come and push and stacking happens, and then the exception handler will do, and then retrieving data is by using pop instruction. You retrieve the data and you'll run the next. So then get the current PSP value of T2, then retrieve the context of T2 from the private stack by using pop, that's context retrieving, and then run T2. So this is the flow, how the switching, context switching, and how the saving and retrieving happens when a task is scheduled to run. So this you learn from the previous session, stacking and unstacking. So you are in a thread mode. Normally it runs the task 1, and when that allocated time period finishes, it has to go and save that locations into this task 1. Stacking is nothing but it's pushing by push data, so it has to push on a full descending mode, so R0 to R3 and R12 LR. In this fashion it pushes, and then it goes to the exception handler, and then it doesn't go in the normal function. It goes to popping out of the retrieving data and goes back to task 1, but in the round robin we are learning about it will go from task 1 directly to task 2. So in task 1, whenever an exception happens, again it will be stacking and going to exception handler, and it will load all this value into the stack registers, and all the contexts will be stored in this fashion. The return address, because the link registers will have all the addresses, and it will point out to the program counter where it has to go. So these registers will be really handy to program. And in this case, round robin, it doesn't do the unstacking, or it doesn't go back to the normal function, back to task 1. Instead it goes to task 2 to operate. So this is how the stacking and unstacking happens in the task scheduling. So to recap, it saves everything into the private stack counter, and it saves all the information and goes to task 2, performs its function, and then comes back to task 1 at the end. So this is the stack frame. The stack frame consists of all these registers: the program status register, the return address, which is nothing but the program counter, the link register R12, R02, or 12, and these are all general purpose registers. So R0 to R12. First, when you load, it will come as a stack frame 1. So initially it will load all these that on the frame, and what is not on the frame you have to push it manually to store. For example, if you want to store R4, R5, R4 to R11, then you need to push that manually, and the stack frame and the stack pointer, you have the status register and the counter as well in the stack frame. So this is, we learned from the previous session how to generate that 1 millisecond. This is all the values that you got to go for. The processor clock runs on 16 megahertz. To run on a 16 megahertz count clock, to create 1 millisecond, that runs on a 1 kilohertz frequency domain. So 1 kilohertz is nothing but 1 millisecond. To bring down to the real system timer count, how many counts it has to be to start with the loader on the system clock, and it has to be on the processor and the system clock. So the reload value, when you put that into calculation, you get the number of value to be loaded, it's 16,000, and you got to load that into that and to get this to generate 1 millisecond. So this is a formula you learned already. And going further, if you want to change the count, then you got to change the delay as well. So for one count, it takes 0.0625 microseconds, and 0.06 microsecond delay is considered as one count. For 1 millisecond, you need 16 times of that 16 count. So therefore, if you want to generate 1 millisecond, it's 1000 times of that is the millisecond delay. So 16,000 count. Micro is 16 count. Microsecond delay for one count, it's 0.0625 by the calculation. Now we're going to learn about how you can save those context of the task one in the stack frame one. As soon as the task scheduler starts to happen, it will save everything on the private stack on task one stack area. That will be after the end of the SRAM end, then the stack area starts, and then the stack 2. This is how the context is saved when it wants to jump to perform task 2. This is how the stack 1 frame will be saved in this context. By default, it will save all of these registers in the stack frame 1 by using the push instruction, as you know, stacking all this in this fashion. And then the frame 2 will be one after that. Once it wants to go to the frame 2, it saves those data in this particular frame into the private stack, and then the stack 2 be informed. So save the value of PSP. It is required later when processor need to resume the execution of T1 by retrieving its saved state. So store everything in the global variable, so it can be used for when it returns back to that state. So this is how retrieving happens. So likewise, when you want to retrieve data, it will go back to its current primary private sector stack, and this will pull out by pushing out information out from retrieving. So it pushes T2 out first, and then T1 likewise. So this is how the retrieving context of the stack happens, frame 1 and frame 2. So first SF1 and then the SF2. That's SF1. Stack pointer will be there. The unstacking, you also learn that on a normal function, when you do the unstacking, you use pop instructions to unstack it. And likewise, you also stack here as a frames, stack format 1, stack frame 2 before moving into the tasks. So initially, to start off with any program, it will be declared with a dummy stacked frame. So nothing will be there. You need to put something in and start as a dummy. So each task can consume a maximum of 1 kilobytes, which is what we're going to learn today as a private stack. So the stack will be used to hold all the local variable contexts. That's the stack format 1 and stack format 2 in that 1 kilobyte. When the task is executed for the first time, it doesn't have any context. So the programmer has to load the dummy SF1 and SF2 for the stack initialization, which you will learn that in the scheduler. And this is how the dummy initial context is. So the stack initial context in this format, all these default registers, and then the SF2 of these registers. First, you got to load the link register and the program counter and the program status word, then followed by the registers. Now let's learn about what is a program status register. The program status register is a 32-bit instruction set, and if you want to read any data value, then you got to use MRS instruction to read, and to write you need to use MSR instruction from that. So in a 32-bit, the first 0 to 26 bits are all for reserved. The next one is for all these registers: the application program status register, the interrupt program status register, and the execution. And this is the program status register. So as soon as you load that via the stack frame, so this bit has to be enabled to keep that's the program counter PC counter 15. So when you do the math, and you will get this value, you got to do that, and you need to specify the address of the task to handler when you are on task 1, the return address. And the link register will have the exception return, which contains the exception exit as well. It will have a special value. So this is how the task stack knows that which task to do and where to return to, and everything, all the value, everything will be holding inside the program status register, PSR register. So, and the execution return behavior, this is all we will be following, but one specific register, that this is the one which is serves for our purpose. So return to thread mode exception returns, because this one doesn't use a floating point unit state. So this is the one we need to use. The others, you can also use this PSP, but it has a floating point unit, which means a floating data, which troublesome sometimes. So for the execution return, you need to use this address to tell the controller to go back to this address. Now let's get into the programming, and I'll show you how these tasks can be scheduled with sysdig interrupt. Before that, I'll give you a short break, so go and relax and get something to eat and get your energy back. And when you come back, I'll show you from scratch how to write this program. I'll see you in a tick. See you then. Bye now.